Recording. Okay, it's a pleasure for me to introduce Professor Matthias Baaz from the Vienna University of Technology. Matthias Baaz is a famous proof theorist, and he is also famous for organizing very important conferences, for example, the Gödel conference in 2006, when I remember, and he's also secretary of the Kurt Gödel Society. But anyway, today he's speaking on the benefit of unsound rules. Please go ahead.
Thank you. So I'm very grateful that I'm invited to this conference because I always admired the work of Professor Orefkov. Now, Professor Orefkov might not be so visible to the general world, but he has very important results. Which may seem simple afterwards, but are very difficult to find. So, for example, in this lecture, I especially selected this topic for the lecture because it uses one of Professor Orefkov's results, namely the non-elementarity of cut elimination in first-order logic, which is an astonishing result because it shows that cut elimination in first-order logic is a very finitarian thing, is a limit case of the general cut elimination result of the infinitary case, where we have epsilon zero as limit ordinal for the Bernoulli arithmetic. But here, this stack of twos occurs. So on the benefit of unsound rules, this is a little bit a more provocative topic than that one I selected first on Ender's colonization, but I will also explain this. So let's start with the history. The most famous book in mathematics is without doubt the Grundlagen der Geometrie of David Hilbert, with which he started the axiomatic method. The axiomatic method led to the Hilbertian revolution in mathematics, which is so profound that we maybe forget how it was before. So what is the kernel of this revolution? The kernel of this revolution is the definition of proof as a sequence, or you can also make a tree if you like, as a sequence of formulas where every formula is either an axiom or follows by direct rule application from the formulas with lower index, and the last formula is a result that everybody learns, even in school. And everybody thinks it's very fundamental. It is maybe ancient, but it is not ancient. It comes from the last century. And with all revolutions, it is so that they tend to go to the other extreme. So for example, we know that Darwinism is correct, and therefore we completely overlook Lamarckistian aspects. Even the Royal Society made a conference on Lamarckistian aspects recently. And the same happens with the axiomatic method. It is, of course, the method of choice of mathematics which led to the unreasonable effectiveness of mathematics as it in the last decades, as it could be called. But there are cases where one could go away from this paradigm, and I will speak about such a thing. So how it looked before. So let's see a famous ancient proof, which was not a real proof in our sense, namely the argument where Euler became famous, namely the derivation that the sum of n divided by n square is p square divided by 6. So how I did it? So it is a very hilarious reasoning, very famous. And I think many of you know it. It occurs in many books, for example, in Polya's book and so on. So consider a polynomial of even degree. And if this polynomial has 2n roots plus minus b1 bn unequal 0, then we can simply, this is elementary school algebra, rewrite it as b0, 1 minus x square divided by b square, b1 square, and so on and so on. And now we compare the coefficients and find out that the b1 is in fact the sum of the b of the square roots of the roots. And from that, now Euler concludes. We look at the Taylor series of sinus divided by x. Then it has roots plus minus b plus minus 2b and so on and so forth. And now by analogy, Euler assumes that the infinite degree polynomial behaves in the same way as a finite polynomial. Hence, we have the product representation. Finally, we get the second coefficient. And the second coefficient sums up 1 divided by b square, 1 divided by 4b square, and so on and so on. And this gives, in fact, that it is b square 6 is the result that could not be guessed. And of course, we would not accept this proof anymore nowadays. But don't forget, if you know that it is b squared divided by 6, it is easy to prove. You find, for example, in the book of proofs a proof, but if you don't know, it's hard. And this is maybe the significance of that argument. Now let's look at another such things. This is now modern. It goes back to the work of sorry, this is only the structure. This is by the way, the work of me and Johan Aguilera during his PhD. This is one of the things that were done. He is now in Ghent and in Vienna. And so let's look at this. That Kurt Gödel is Austrian and tells that Kurt Gödel is Austrian. Fine. Hence, that Kurt Gödel is Austrian and tells that everyone is Austrian. Not good. That is, if Kurt Gödel is Austrian, then all people are Austrian. That's okay. And therefore, there exists a person such that if that person is Austrian, then all people are Austrian. That's okay again. So the interesting aspect here is the result is correct, but the sub-derivations are not. And logically, it looks like this. And so we see, we apply the universal quantifier in a mutilation of the eigenvariable condition, because the A is on the left side. Okay, but the result is sound, as is correct. So, and this has to do with the Hilbertian form of proof, because we go now away from the Hilbertian representation of proof, where inferences are sound. That means only true conclusions result from true premises. And derivations are hereditary. That means initial sequence of proofs are proof over themselves. But that's not necessary so. So we propose another concept. And this concept is based on a one could say liberalized eigenvariable condition. We will see. So here we still have this weak regularity. That means one eigenvariable or characteristic variable occurs only one in such a strong quantifier derivation as universal right or existential left. Normally, the regularity is the reason why Gentzen changed the Hilbert sequential format to a tree format. The interesting aspect of the tree format, which is very much, which is of course known to us all, but it is not completely fitting to mathematics, because you can easily imagine the situation that you prove the same result twice when it occurs on two different branches. No mathematician would do that. But because in the Gensen argument and in Dutch proof theoretic arguments in general, you need regularity, and therefore the read format gives you this regularity. It is obvious. You can simply rename the variables under the usual eigenvariable conditions. And now we depart from these eigenvariable conditions. And to have this concept, we first have to introduce the concept of side variables. So side variables are simply variables which are standing in the formula, and they are not the variable where the inference is made. Strong inference. For all right, they exist left. And these side variables are ordered by a relation that simply means that B is a side variable of A, means that A is less than B in this proof. Another thing we will need later, and which should be introduced now, is colonizations. Colonization in my, this is in mathematics, in logic used in different contexts, but here I use this colonization in the proof theoretic sense. It means simply as a replacement of eigenvariables by suitable function terms. Any normal, for example, cut, or in proof even with cuts in LK can be colonized such that the end segment is colonized simply by replacing the appropriate eigenvariables by suitable terms. The question is, that can be done always. The question is only, can it be reversed? So it can be, for example, reversed for classical logic, for LK, but not for intuitionistic logic, LG. So this is this colonization I will speak about. And now the suitable quantifier inferences. So we have now a changed eigenvariable condition. We allow the eigenvariable occur in the conclusion. But we have three conditions. The first condition is that the eigenvariable may occur in the conclusion, but not in the conclusion of the proof in the end sequence. The side variable condition, this order I introduced is acyclic, and the weak regularity I already spoke about. The weak regularity is in a certain sense the weakest condition of the three. And the calculus LK plus is defined by these three conditions. And, sorry. And we can also define a second calculus. That is when we ask for even weaker regularity, namely when the same variable should appear in the inference of the same formula. That means it can appear more often. A recent result shows that the both calculi LK plus and LK plus, I mean the cut-free parts, they simulate each other elementarily. So for example, an LK plus proof is of course an LK plus plus proof. This is less restrictive condition. And the condition of the LK plus can be double exponentially simulated by LK plus plus. This will be important for this Andrews colonization. I come to that later. So now let's look at soundness. This thing is sound. Why it is sound? This is maybe the most funny thing. Why it is sound? It is sound by the following argument. This argument is partly due to an anonymous referee we had another argument that was more complicated, but this is much more elegant. So what we do is we simply do not do these inferences. That means instead of concluding for all xax, we take AA implies for all xax to the assumptions. Under that circumstances, we can translate the whole proof. And in the very end, this order of the side variable conditions makes it that we can cut them out by one, because on that A, in this A of A implies for all xax, we can introduce an existential quantifier if A is an eigenvariable in the sense of LK. And the side variable condition tells us that we always find such a maximal side variable, and this cannot occur as side variable otherwise. So the eigenvariable condition is fulfilled. And what is the difference between LK plus and LK plus plus? In LK plus plus, we have to contract them because this can happen more often. And then afterwards, the formula that exists in X, A of X implies for all xax is classically valid, can be derived and cut it out. Therefore, the whole thing is sound. Observe that it is not a soundness proof by induction on the length of the proof. That is not possible. And observe further that it introduces cuts, even on the cut-free proof. Yeah, it introduces cuts. But as LK is sound, LK plus and LK plus plus are also sound. Now, here, this is an example that shows that this side variable condition, so the order, the acyclicity of this order is really important, because if we drop the acyclicity, we get the following wrong inference. So this is exactly, all the other conditions are fulfilled. The eigenvariable do not occur in the conclusion of the proof. And of course, the regularity is also fulfilled. However, we see that the eigenvariable, the side variable condition oscillates, and therefore we can derive for all y that exists in X, xy implies that exists in X for all y, xy. That is, of course, not correct. So this is only to show that we really need this order in the side variable condition. So the next is now the question for what? So good proof theory is theory of proofs. This is more theory of proofs in the sense of the speaker of yesterday. In the sense of Kreisel is more theory of proofs. But good proof theory has an effect. So proof theory for the aesthetic of it is useless. To invent calculi after calculi for the beauty is maybe not satisfactory. And therefore, we will have a strong result, and that is connected to Professor Orevkov's work. So let's first look at this example. We prove something, and believe me, this is the shortest proof in LK, and this is the shortest proof in LK plus. Okay, this is an example. An example says nothing. Is there an example for, or it says something, but it is, so to say, no general hint. But in fact, we will prove that there is no elementary function bounding the length of the shortest cut-free LK proof of a formula in terms of its shortest cut-free LK plus proof, or LK plus plus proof. This doesn't matter after what I said before. And this is, so to say, something that is strong. And for people who like as applications, also applications are always a doubtful motive. for people who like applications, one could think that this is an analytic format which is under never longer, but sometimes very much shorter than the usual format of eigenvariables. How we prove that? So the first thing to do, this is a difficult thing, but I can motivate it, is that we introduce as an intermediary calculus, a calculus where we can shift around the quantifiers. This is something with an old meaning in proof theory. Then maybe you remember that the error in Herbrand's proof, Herbrand's theorem is some sort of a curse theorem, because very often people want to prove it in full generality, and usually it is false. Herbrand stated it in the full generality of infix quantifiers, without column functions, without anything, infix quantifiers. And to prove it, he used to prefix the quantifiers. And he did not observe, and this was discovered much later, that the shift of quantifiers strongly changes the Herbrand disjunction. And you could derive from this work that it changes under some circumstances. As here again, easy examples can be found. For example, for all x there exists in y, ax implies a y against the existing y. For all x, ax implies a y. As one has Herbrand disjunction length 1, the other one has Herbrand disjunction length 2. But from this work, it can be that it inferred that the difference is not even elementary bounded. Yeah, so you can, by reshifting quantifiers, very strongly change the proof. So to say, the LK proof. And this means that the shifting quantifiers, a very natural method of proof for humans, is on another level than the usual proof theoretic calculus. So let's look at this intermediate calculus LK shift, which simply represents all quantifier shifts. And the basic point is that, that LK plus simulates LK shift double exponentially. I mean, you would of course say here, easily I speak with double exponents, which is already the deathbed of computer scientists. Yeah, double exponent, the things are gone. But here we are speaking about non-elementary differences, and therefore this is justified. So that means that this new format of eigenvariables is able to produce these quantifier shifts, which are astonishingly maybe an extremely strong method of proof. Okay, so, and now comes Professor Orevkov's work in. There is no elementary function bounding the length of the shortest cut-free LK proof of a formula in terms of its shortest cut-free LK shift proof. Yeah. So what we do, we take Professor Orevkov's sequence. We can also take, of course, other such strong growing sequence, but Professor Orevkov discovered them. The size of the SE is polynomial in E. There is not bound on the size of the smallest cut-free proof that is elementary in E, so this goes over 2 over 2 over 2 over 2 and so on and so forth. The set of these proofs, however, with cuts is polynomially bounded, and which is not in Professor Orevkov's proof. We can assume that the cut formulas are closed. That means they are Brenex. This can be done easily by additional cuts, because additional cuts make this shift. So the effect of the quantifier shifts is on the cut-free proof, this strong effect. And now we do the following. We transform this proof in LK shift. And our idea is that we, so to say, put the quantifiers in the worst position. That means if we have for all x, ax implies for all x, ax, we put for all x that exist in y, ax implies ay, y. Because then, if we scolemize this thing, as I said, it will depend, the Scolam function will depend on the universal quantifier. It is, in that case, the existential quantifier is strongest, it's on the negative side, on the left side of the sequent. So the universal quantifier is V. And so this is the position which is, one could say, the weakest one. And if we scolemize this, we see that it takes the form, let's say, a x implies a f of x, and so on and so on. Now, if we have, then this is a cut-free proof. We moved all cuts to the antecedents. The proof is cut-free. So we get a Herbrand disjunction, elementary. The Herbrand disjunction, maybe it needs an exponent, but in generally, the Herbrand disjunction can be immediately read from the cut-free proof. Now, how the things look there? It looks then AT implies AF of T and so on and so forth, of course, iterated with all the prefix. And now we make a transformation. We take the biggest such column term, let's say FT is the biggest one, and replace it by T, and continue and continue and continue and continue. And then all the Herbrand disjunction is a tautology. So therefore, replacing a term everywhere by another term doesn't change this matter of fact. So therefore, this column terms shrink and shrink and shrink. And finally, the formulas in the antecedents become of the form B implies B, propositional. Now, B implies B propositional, this is a true sentence, and does not change the truth of the Herbrand disjunction. That means we can discharge these things. And therefore, the Herbrand disjunction has to be very, very large. Yeah? Because if the Herbrand disjunction would be shorter, we could reconstruct the old cut-free proof from it, which is relatively short. And this is the reason. So it depends on the fact that these new eigenvariable conditions are more or less as strong as the shift of quantifiers. At this position, you might ask why this is of any practical importance. There's a very strange thing. I will describe it. In the beginning of automatic theorem proving, the people thought, we cannot prove much. So whether the strategies are complete or not doesn't matter anyhow. We cannot prove much. Yes. It turned out that never ever a strategy worked that was not complete or where it was not clear on which subclasses it is complete as input. And the same thing is with these results. Of course, the non-elementary bad case needs complicated constructions and is rare, one could say. But everywhere where this non-elementary bad case occurs, also in general, it is bad. So for example, the example I gave before shows that to make the quantifiers Brennex in an unlucky way might increase the length of the proof enormously. And now in automatic theorem proving, they found this. This was only maybe one exponent where they looked at, but it was the same. So they decided to apply this columnization without prenexing the formulas. And so this is in general. So the general very bad result in the first order logic, as a very big difference in complexity and so on, has a shadow, a real effect on the practical level in the low region. Why this is, I cannot answer, but it is a phenomenon that is well known in automated theorem proving, for example. Now, let's look at the negative consequences this has. So we can, for example, not columnize such a cut-free LK plus or LK plus proof without introducing cuts. With cuts, we can. This columnization always says for all x is replaced by f of whatever. But this needs additional cuts. Why? Again, for this argument. If it would not need additional cuts, we could reconstruct a shorter cut-free proof from the columnized version. And now comes something in which really fits to this calculi. Namely, in computer science, something is known which is called Endros columnization, and that says make these column functions only dependent. So again, we replace strong quantifiers, as in automated theorem proving. This is of course refutation. So these are the existential quantifiers. Replace strong quantifiers only by column functions depending on the weak quantifiers that bind in the formula, but not depending on the weak quantifiers only where it is in the scope, as with usual columnization. This is Endros columnization. One can easily motivate this Endros columnization by structural translation. So, but here we can motivate it simply because we can do it. We can take this cut-free proof and introduce Endros columnization. Namely, we take the LK plus proof, get Endros columnization. Then we look maybe at the resulting cut-free proof, and we descolumnize. And again, we can descolumnize. Here, we can descolumnize in LK plus, but LK plus by LK plus because we don't know where these column terms are. But LK plus, so to say, simulates elementary LK plus. And this means that Endros columnization in resolution refutation has cases, or a sequence of cases, depending on Professor Orevkov's result, where it is non-elementary better than usual columnization. That follows from that. Of course, nothing is positive which is not also negative under certain circumstances. Namely, the whole thing will not work for intuitionistic logic. Already, this is an example, because this is obviously a proof with the intuitionistic restriction of the sequence on the right side. It's a proof in LK plus. And it has a result that is for sure not valid in intuitionistic logic. So the cut cannot be eliminated in intuitionistic logic. That is obvious. Yeah, and from that you can also derive an interesting argument, namely that Kreisel would say I should add interesting for me argument, that the Gensen algorithm or a Gensen-like algorithm can never work on such calculi as LG and LK and LK plus plus, because it would treat intuitionistic and non-intuitionistic proofs the same. There is no difference. Yeah, and the result is, so to say, behavior of this algorithm is the same. And here it is not possible to remove the cuts. And the reason of this is exactly has to do with the simulation of LK++. Of this shift calculus. Namely, it turns out that this type of calculi produce all possible quantifier shifts, even in the intuitionistic case. And there are exactly 3 quantifier shifts that are not valid. Intuitionistically, 3 classical quantifier shifts. These are the 3 they are well known. What LG++ would be, or LG plus, is simply the addition of all classical quantifier shifts to intuitionistic logic. Of course, I don't know what is that. So there are these things I already mentioned them. And in the end, I want to discuss what is the origin of this calculus. Namely, the point is he has some aspects of the epsilon calculus, but not all. So the calculus LK++ in its behavior corresponds exactly to the epsilon calculus. You can, of course, write the epsilon calculus not in the Hilbert style calculus, but you can write it as a sequence and it would look like that. Reasonably, you should introduce a tau for the symmetry. Hilbert was, of course, proud of not having tau because epsilon is good for everything. It simply describes the universal quantifier. And if we see then, this is exactly this behavior of the eigenvariables. The order of the side variables come from the inner structure of the epsilon terms, but the epsilon terms are here and there, doesn't matter. This extended eigenvariable condition, and of course this weak regularity also follows because of course different formulas have different epsilon terms. But there is of course one important aspect of the epsilon calculus that is not covered, and this is the ability, and this is maybe the most strong property of the epsilon calculus, the ability of the epsilon calculus to make inner inferences. You can simply overbind bound variables. This is also the way how the epsilon calculus produces expressions that have no first order meaning. Yeah? You simply take the existence x unequal x is equal to the existence x unequal x. This is a translation of for all x is equal to x. And from that you derive by one critical formula the existence x unequal x is equal to existence y, existence x unequal x is equal to y. And the second epsilon term has no meaning in classical logic. And this does not matter, of course, for the epsilons, as anyhow they can be eliminated, but one should not forget this. And these inner inference properties are not represented by these two calculi. So in the end of my lecture, I want to discuss this in a general setting. There might come a time where for special applications, not as say in general, so it's very false to ask for the generality of such concepts. There might come a time where for specific application in mathematics, one will tend to such global concepts of proofs again. To such global concepts where the subproofs are not proofs. so to say, the subderivations are not proofs. But the whole thing is correct. And this was only one aspect where one uses this. There are many other aspects. I give you, for example, another example. So, for example, you could, in propositional logics of any kind, Professor Fitting will agree, you can form macro functions. So everybody knows that A equivalent B is A implies B and B implies A. Yeah, so you can make this macro, and in reality you can take simply, if you have any sequent calculus, take the rules for the inference of this macro, and this is the inference of a new operation, let's say the equivalence. This works, but does it work in first order logic? It does not work in first order logic, because consider, for example, the very simple macro for exists, for all that exist. And consider, for example, for all x exist in y, axy, implies for exist in x, for all x exist in y, ax, y, or z. We cannot form an inference which represents this for all they exist in one step, simply because the eigenvariable in the usual AK block each other. Yeah? You can make neither the left nor the right inference. And therefore, in that case, you also need such a liberalized eigenvariable condition. A similar liberalized eigenvariable condition occurs if you, for example, want to formulate subsystems of Hankin quantifiers, not because the Hankin quantifiers speak of subsystems. We're not speaking about subsystems. In the whole proof theory, subsystems of second order logic are considered. Yeah, we're not considering subsystems of Hankin quantifiers, which one axiomize, which one have search for proof theoretic calculi, and so on and so forth. And then, not because the Hankin quantifiers are so specific, because they are a macro, such eigenvariable conditions are needed. And this is only a very simple example. Maybe there are much more complicated examples of global proof concepts. And maybe there are opportunities to explore them, and maybe they are of some help somewhere in mathematics. And in the very end, I want to thank Professor Orevkov for his results, and I want to cite again Georg Kreisel, who said to me that logic is a set of results and methods which are maybe not very remarkable if you know them, but they're extremely harmful if you forget them. And this applies to this non-elementary of cut elimination for sure. Thank you very much.
Yeah, thank you very much, Professor Baaz. Now it's time for questions. So who wants to pose a question?
There's a huge, can you hear me?
Yes.
Yes.
There's a huge development of treasure trove of actual mathematical proofs now from the proof assistant community. Thousands and millions of lines of proofs, some of which you can retrieve and actually possibly examine, others of which are just simply code. But I was wondering if one can use the kind of thing that you work on to make sense of this treasure trove, or use this treasure trove for additional examples of phenomena, because the people doing this, this proof assistant stuff, I don't think pay enough attention, don't pay serious attention to proof structure. They just want to say that they're heroes, that they managed to get stuff actually proved. And rather than trying to ferret out interesting phenomena of these actual proofs.
In fact, I am convinced that this is the right way to look at the things, because this also explains the big civilizatory clash between mathematicians and computer scientists. The mathematicians are more or less, in most cases, I do not speak of limit examples, like for example, Hale or something. In most examples, know that their proofs are correct. So they ask themselves for what they are made formal. And even Hale told me that the point of making this proof formal was that one had to rethink it, and afterwards one would not need its formal verification when one has understood it. So it was some sort of a disciplinary exercise to make this formal embedding for Hale in the proof verification system. Now, this is very, very true, and I find also that that one should automatize these things, because all these proof theoretic analyses and such work in some cases and not in all. So one has to search the proof, and maybe this automatization would help this search. I agree to that.
But the one thing I've been curious about is, I mean, these proofs are generated through the guidance, most of it. There's some automated generation, but through the guidance of somebody sitting at a computer, pushing the computer to accept a proof idea. In other words, there's a human brain behind getting the machines to accept these proofs, and the machine is in some sense filling in a lot of the details. But the overall structure and the way it's done is humanly driven, and it may not correspond very well to our current proof theories, because the humans are just using anything that they can get the machine to accept, and they don't want to actually die in front of a computer, so they have to actually develop some tricks and some things. In other words, it's all done it all seems to be done very independently of serious proof theory. That's what I'm trying to say.
Yes, it is very true, but it remains that there are aspects which are not so visible to the humans. For example, the sigma 2 Herbrand disjunction. The sigma 1 Herbrand disjunction is visible. The sigma 2 is not. So one could use such aspects. It means you are completely right. If one would do that, one had to search for the aspects which are not in the human vision, one could say, or not yet in the human vision. That would it be.
What are the prospects? I don't know the state of the art. What are the prospects socially in terms of proof theorists, in the sense that we mean, working with the automated, with the proof assistant people to get some common ground and research going of the kind that you and I are talking about now?
I think it is not so bad. It is my theme, because first of all, of course, this is more academic. As I already hinted at, proof theory explains some phenomena which are strange or unexplainable. So you could say, okay, if you do this concrete technical manipulation, then on the level of the proofs, this is that, and this has enormous consequence. This doesn't mean that it has there, but as I already said, in automated theorem proving, at least it is accepted that that something which is, so to say, theoretically not well founded doesn't work either. For some reasons, I do not know. I have no explanation, but it is a matter of fact, and therefore these people would not, so to say, despise it and would go back to theoretic investigations. Because at the first glance, you could say, make a proof that means, naja, I have this technique, then I refine it, then I try this, then I try that, then what works that I take. There are many fields where this is done. So, for example, I had a friend who were in a company of numerical analysis, a practical company. So he said, okay, when he has a problem, there are 10 methods we try, and which works we take. But that is not in automated proving, theorem proving. There very often comes a moment where you want to understand why these things have an effect. So this is the first thing, and the second thing is that you simply come sometimes to some sort of a limit. So, for example, as Sam Baaz said in his talk, one doesn't know which variable one should add. And if you think the adding of variable is the cut, I mean, the atomic cut is nothing. But if you have these explicit definitions, then it is an arbitrary cut. And in a certain sense, it is the addition of a cut. So the question is how to find cuts, for example, and that is already a question of the theory. And so I see that. I see this relation not as bad. Generally, if a field is new, the people tend to disregard the theory. So, for example, in machine learning, in artificial intelligence, they say, oh, why should we bother ourselves with this and that? And so we do. But after a certain time, this changes because they see that the theoretic results have a connection to the practical behavior of the things.
I was also kind of fascinated by, we know that there's this huge blow up with cuts that goes way back. I don't know, exactly how far back that goes, but we have these ridiculously huge lower bounds. The question is, one question I have is, how good are we at spotting some really interesting examples of a highly mathematical character where there's blow up?
Yeah, there's first an answer. So one could of course ask why in these extreme bounds need as your results on independence need highly sophisticated constructions and do not occur in practice. Now, contrary to let's say the independence, here is a practical answer. But that comes not from the cut elimination of Gentzen, but from the epsilon theorem. The epsilon theorem is nothing else than the contraposition of all case distinctions in the proof, and this produces the Herbrand disjunction. Now, humans hate case distinction. Consequently, in the proof, there are few, and that means to find these mathematical examples, one should look at the situation where, for example, many case distinctions are absolutely needed, also the humans don't like them. And another source is that that the humans always know when they use a lemma, what is the lemma and what is the implication of the lemma. Whereas in the card elimination procedures or in the cards, this is completely symmetric. And that means only in these cases, one can look at Oreskhov's example. There one sees it easily. In Stedman example, one see more the construction over this Landakar is a combinatory logic system. But in Oreskhov's example, one sees it directly, that it needs the symmetry of implication and being implied. And again, if you want to have mathematical examples for that, one should look where it's absolutely necessary to have this symmetry. This would be my guess.
Okay, so
I think I'm going to stop asking questions so you can go on.
I guess Sergey wanted to ask a question, right?
I have a small question. So basically, I formulated it as Sergey Artyomov. I'm sorry.
No, you can ask a question
But
too.
I wrote actually the question I sent to everybody, so you can see the question on
in the chat or what?
Yeah. So yes, in
If
discussion.
I could see the chat, I could see it. Tell me the question. What was the question? Tell me the question.
So the question is, I mentioned Shining, who asked often about powerful admissible rules. So it's a good thing, but it's very different from structural link between derivable rule and basic rules. Maybe the rules you consider, some of them at least are admissible in some subsystems.
Probably, yes, probably. It depends on the position of the variable. So if one variable class, it might be that they are admissible. Yes.
So just I'm curious.
Because
yeah.
Sorry, because you see, if you have only uniterated quantifiers, then this order of the side variable condition doesn't play a role. Only to answer this question.
Yeah, it's okay.
Yes, I should check it.
Yeah, Sergey, now the question is, there are two more questions and we are running a bit out of time. So what should we do? Should
I'll try to be very quick, but there are two questions. The first, it may allow just a very short answer. So the new flexible proofs, they are targeting more admissible rules to become existing derivations the existing derivation toolkit more efficient, or there are certain situations where they're absolutely necessary to do the right derivations. The system doesn't work without. So it's the first prediction. And the second small question is, any Daniel Shamkarov cyclic proofs, do they fit to your paradigm of a non-standard flexible new type of flexible proofs?
They fit to these paradigms. Yes. They are also global proofs where there is so to say, where the subproofs are not proofs themselves, what is obvious. Yeah, they fit for sure.
And so the first question is, the flexible proofs are to make life more efficient, or there are some situations when you cannot do without?
They are to make life more efficient.
Yep.
This is simply so that under some circumstances, such things might be superior. I mean, you lose the inner inferences. In the normal mathematical proof, you can say my lemma is also a result. Yeah, here the lemma that is a cut is no result.
Yeah.
No result. So, but the whole thing could be more efficient because of that.
Absolutely. No, I got my answers. Thank you. So
yeah, so there's a final question by Professor Gerasimov. Do you want to ask a question?
Yeah, Matthias, how do you relate the quantifier rules of LK plus with Hanel and Schmidt's liberalized delta rule in free variable semantic tableaus? I wrote this question in the chat also.
How do they relate? This is a good question. It is exactly so that this makes, in a certain sense, the delta rules superior to the usual form, for example, of resolution refutation, the tableau superior, because also here it is so that you have a certain variable governance which allows you to have such effects. Yeah, so I'm sure that one can show that usual tableaus, in principle, are non-elementary faster than usual scholemized resolution. But of course, you can use other scholemization as a automated theorem proving people do, as Andrews scholemization and such, and then the situation is not anymore. And it will be the same.
All right.
Okay, thank you very much.